Okay, this is exam 2 for physics 102. This covers the latter part of chapter 2, all of chapter 3, and all of chapter 4 except for home circuits and RC circuits. So here first I want to redraw this circuit first of all so that I see it in a more traditional way. And I'll come up to here, starting at the big side of the battery and going around, then come in here and recognize that I have 3 branches that separate, and then on this side they all come back together again, and then I get 2 branches that separate here, and then they come back together again right there. So I'm going to redraw those here. I'm going to have 1, 2, 3. This is my 1 microfarad. Here's a 3 and a 6. And then this is my 1 microfarad right here. Then those all come back together again, and then they come and they break down into 2 branches, come back together, and then they go back to the battery, and that battery was 12 volts. All right, so this is a 2, 2, and a 1. Now there are several things that I can do. I'm going to combine these 2 microfarad. That's going to be, 1 over 1 over 2 plus 1 over 2. That will equal to 1. Then I'll combine these two, this 3 and the 6, 1 over 1 over 3 plus 1 over 6. That's equal to 2. I'll combine those, and then I'll just be left with 2 separate parallel branches. So let's just redraw this again. And that's going to be 1, 2, 1. And 1, 1. And now to find these, I just add them up. So this is going to be a 4 microfarad, and this is going to be a 2 microfarad with 12 volts. Okay, I basically want to know the charge and voltage on all of these. Look, I'm going to show you quickly how we could just reason through this. This is a big capacitor. It's twice this capacitor, so I know it's going to have a voltage that's half, so it's going to have 4 volts, and this would be 8 volts. Now, the way that I would find that is I would first figure out what is the equivalent. Now, you could just stop there, and I would believe that you knew that. But if I find the equivalent capacitance, the overall equivalent capacitance is going to be 1 over 1 over 4 plus 1 over 2. Let's see, that's 1/4 plus 2/4. That's 3/4. That's 4/3 microfarads. By the way, that's the answer here, 4/3 microfarads. Uh, so if I have a 12 and a 4/3 microfarad, 12 volts, then that's going to have a charge equal to CV, which is 12 times 4/3, 12 to the 16 microcoulombs. So that means that this capacitor has a charge of 16 microcoulombs, and this one does too. And I can then calculate by dividing the charge by the capacitance to get the voltage on each of these. But I could have just said, how the voltages are distributed on there. Now, stepping back, I know if this is 8 volts, then I have 8 volts here and 8 volts here. And if this is 4 volts, I have 4 volts here, 4 volts here, and 4 volts here because those are in parallel. And then here, I have 4 volts and 4 volts because these two identical capacitors split up that 8 volts. And then I have 8 volts here. And now over here, I have 4 volts, 4 volts. And this is going to be a little more complicated. Let's see, do I need that? I need C2, C3. Oh, I don't even need that, so I'm not even going to worry about this part right now. But I would have to find the equivalent charge on each of these, which is going to be 8 microcoulombs, 8 microcoulombs, and then I could figure out the voltage, which would be Q divided by C. So 8/3 and 4/3 volts. But I don't even need that, so I'm not going to worry about it. Let's see, so I need to know what is the charge on C4. C4 is this capacitor, so that's this one. That's going to be C times V, or 4 microcoulombs. And then what is the charge on C6? That's this one, which is the same as this one. So that's 2 times 4, or 8 microcoulombs. All right, so that's the answer, 4/3, 4, and 8 microcoulombs. Let's do this multi-loop circuit. I want to know all three currents. So let's target which ones I want to draw the equations for. I'm going to draw an equation for the bottom loop right here and for the big loop. Because notice if I do the bottom loop, I only have one resistor in this branch right here. And if I do the big loop, I also only have one resistor. So it makes it for the easiest equations. Whereas if I did the top loop, I would have both I1 in this resistor and I2 in that resistor in the equation. That would give me an equation with two unknowns, just a little more difficult to solve. So I'm going to do the big loop and the bottom loop. I'll do the big first. Let's just pick some directions for my currents. Doesn't really matter what directions I pick, I just pick those randomly. And now to do the big loop, I'm going to start here and I'll go in that direction. So that's positive 3 minus 2I1. I'm doing the big loop, right? Yeah, minus 2, that's equal to 0. So that's the big loop. Let's do the bottom loop now. The bottom loop, I'll start here and go in this direction. Minus 5I2 plus 8 minus 2 equals 0. So now I get, I can solve these. That gives me 1, negative 1. I1 equals 1/2 amp. And then here I get 6. I2 equals 6/5 amps. Let me pause here for just a second. Okay, so that looks right. I1 then is 1/2. I have I2 is 6/5. And they both came out positive, so that means that I chose I1 correctly to the left, and I chose I2 correctly to the left. Now to get I3, I say, well, whatever currents are coming in have to equal the currents going out. That is I1 plus I2 equals to I3. That is 1/2 plus 6/5 equals I3. What's that? 5/10 plus 12/10 equals to I3. That's 17/10 amps, or you could express it as 1.7 amps. 1.7 amps. And it looks like I chose the direction correctly. So in each of those cases, the direction is as it's labeled, but if the current would have come out negative, then I would have to take the opposite direction. All right, consider the circuit. What is the voltage across R2 and the current through R1? I'm going to start by simplifying this, the 3 and the 6 in parallel. That would be 2. So I would have a 1, a 2, 1, come back. So that's 1 ohm, 2 ohms, 1 ohm, and 6 ohms. And then I combine that 2 and the 1. Now I combine the 3 and the 6. And now I can combine for the final equivalent, which I wasn't asking for that, but it's still useful. So now I can calculate what is the current. So the current coming through here, I, is equal to V over R. That's 12 over 3, or 4 amps. Because I have 4 amps coming through this circuit. That means I have 4 amps here and 4 amps here. That means I have 4 volts R and 8 volts here. That means I have 4 volts here, I have 8 volts here, and 8 volts here. And then I have 4 volts here, 8 volts here, and then this 8 volts is split up. So I have 8 volts over 3 ohms. That is a current equal to 8/3 amps. So I have 8/3 amps here, 8/3 amps here. So V is equal to I R, so I have 16 thirds volts and 8 thirds volts. So let's see what I'm looking for. R2. R2 has a voltage for A, um, 6, 6, oh, I'm sorry, yeah, so this 16 thirds now is also here and here. So 16 thirds volts for R2. And then the current through R1 will have 4 volts across 1 ohm. So I is equal to V over R, or 4 amps. So those are the answers there and there. Okay? All right, if you had gotten some of this right, I would have given you partial credit. For any of these, actually, if you got it right, but the number just came out wrong, I would give you partial credit. Okay, let's look at multiple choice. Capacitance, capacitor has capacitance C. You double the separation and make the area of the plates 1/2. What is the new capacitor? Let's write this. So kappa epsilon naught A over D. And then what am I doing? I'm doubling the separation and I'm having the area. So that gives me a 1 over 2 and a 1 over 2. So it's a 1 over 4. So it's going to be D. Capacitor's been connected to a battery for a long time, has that charge. You double the area capacitor's plates. So it is connected to a battery. That's important. That means that the voltage will remain constant. But if I increase the capacity of that capacitor, then it will now hold more charge. So I am increasing the capacity by doubling the area. So I know that it's not going to be this one, or this one. That the amount of charge that it holds as I make it bigger will increase, and I'm doubling it. So that means I'm doubling the capacitance too. So the answer is going to be A, because Q is equal to CV. If this is constant and I double this, that means I'm doubling this. And the reason I'm doubling C is because C is epsilon naught A over D. I'm doubling the area, so I'm doubling the capacitance. All right, what is the voltage across C1? Well, you could look at this simply and say, well, I have uh, this capacitor has to have the big voltage, 6 volts, and this capacitor has to have half that, 3 volts. I did 6 and 3 because I know 6 and 3 equals to 9, and this number is twice this number. So then the answer would be this. A slightly harder way is to first find the equivalent capacitance. That's 2 fourths plus 1 fourth, that's 4 thirds. That's the equivalent capacitance of those two with 9 volts across 4 thirds microfarads. That's going to be equal to 12 microcoulombs. So that means that I have 12 microcoulombs here and 12 microcoulombs here because, capacitors in series have the same charge. And then if I wanted to know the voltage here, the voltage is equal to Q divided by C. That's 12 divided by 2, which is equal to 6. All right, what is the charge on the 6 microfarad capacitor? Oh gosh, this is the same problem, is it? No, it's a very similar problem. So um, I have 12 volts here, and then I have 12 volts split between those two capacitors. So just like I did before, I know that this is going to have 8 volts and this will have 4 volts. Because I carry the bigger voltage on the smaller capacitor, and that bigger voltage is bigger by a factor of 2, and 8 plus 4 is equal to 12. So the answer then is, well, if I want to know the charge on this capacitor, it's going to be Q is equal to C times V, or 4 times 6, which is 24. That's 6 microfarads times 4 volts is equal to 24 microcoulombs. 5 ohm resistor connected to a battery of 10 volts. What charge flows through it in 2 minutes? So I is equal to V over R. That's 10 over 5, or 2 amps. So 2 amps. Q then is equal to I times T. That's 2 times 2 minutes, which is 120 seconds. 2 amps times 120 seconds. That's 240 coulombs. So the statement says necessarily true. That's true. It is always true. The current through an ammeter is small. That's not always true. The current through a voltmeter is small. Yes, that's always true because the resistance is big. And ammeters are not hooked up in parallel. So the answer is D. Okay, you have a circuit with a single resistor and a battery, and plot the following graph. The slope of the graph is 2. What is the resistance of the circuit? Okay, so several ways you could approach this. It was made a little harder. We've seen similar problems, but this is made a little harder by not having numbers. So you have to actually interpret the slope in some way. So, uh, well, probably the easiest way is to say that V is equal to IR, and then I rewrite this in terms of the slope of a line because I have current here, 1 over R times V. That's the same equation, but I've written it in the terms of my dependent and independent variables. So then my slope is equal to that. So my slope, which is equal to 2, is equal to 1 over R. That means R is equal to 0.5. That was probably the easiest way, but you could have done some stuff where, you have your slope is equal to what? I over V, rise over run, and then how does that then you could have said, well, that's 1 over R is equal to I over V. So you could have gotten it in that way too. Which is a bigger resistance, a hairdryer or a light bulb? Well, P is equal to V squared over R. So the one with the bigger resistance is the one with the smaller power. So it's the light bulb. If a 100-watt bulb is connected to your house with a voltage of 120 volts, what is the current? So P is equal to V times I. That is 100 equals 120 times I. So I is 100 over 120. That's 0.83. And a current of 20 amps flows through a wire of length 1 meter and radius of zero point 0.5 millimeters. The potential across the wire is 0.32 volts. Okay, so I need to calculate rho. That's R uh, L over A. I started with this equation, rho L over. That's what you have on your equation sheet, and I got it wrong, didn't I? So it's going to be R A over L. But first, I need to figure out what is R, because R is equal to V over I, which is going to be 0.32 over 20. You get 1.6 ohms. So now I can figure out what is rho. I get 1.6 ohms times the area, which is pi times 0.0005 squared divided by the length, which is just 1. That's convenient. And then you get that that value for rho is equal to that. So that's going to be your answer. Two wires A and B are made of the same metal. That means they have the same resistivity and they have the same length. But the resistance of wire A is 16 times the resistance of wire B. That means, by the way, that they're going to be different diameters, but the one with the bigger resistance, that would be this one, is the one with the smaller diameter. So wire A is just going to be smaller than wire B, so I can get rid of these. But remember, this is rho L over A, or I could say that it's rho L over pi r squared. So if I'm a factor of 16 over here, that means I'm a factor of 1/4 over here for R diameter. So D is the right answer. The circuit, what is the voltage across R2? We've done this, um, sorry. So I need to find the equivalent resistance here. 4 and 4 in parallel. That's equal to 2 ohms. That's equal to 1 ohm. Oh, this does not work out easily for me, so I'm going to have to figure out what is my equivalent. That's 3 ohms and 10 volts. That means that my current, I, is 10 over 3, or 6.67. That's right. No, I'm sorry, 3.33. I'll say 3.3 amps. So that's my current there. That means I'm going to have 3.3 amps here and 3.3 amps here. And I'm looking for the voltage across R2, which is going to be the same as the voltage across here. So that would be 6.7. If I did 3.33, make it 6.7. Consider the circuit. What happens if you remove R1 to the voltage across R3? If I take out this resistor right here, the resistance of this part goes up. That means that the voltage of this part goes up, which means the voltage of this part decreases. So B is the right answer. Consider these three circuits. Rank the 4 bulbs from the least to the most brightest. Well, imagine if I have 12 volts here, 12 volts here, and 12 volts here. Well, I would have 12 volts here, and I'd have 6 volts here and here, because they'd split up that 12 volts. Here I would likewise have 6 volts and 6 volts. Here I would have 4, 4, and 4 volts, because it splits up that voltage 3 ways. So the one with the highest voltage will be the brightest. Oh, that's D, that's all of them. And then C, looks like C and A are the same. So I can get rid of that, and it's next. Oh yeah, so E is the right answer. C and A are the same brightness, B is the least bright, and D is the most bright. Voltage across the 1 volt resistor is 1 ohm resistor is 3 volts. What is the voltage across the 6 ohm resistor? So a couple ways you can do this. I could just say this is 6 volts. It's twice the resistance, so it has to be 6 volts. 3 plus 6 is equal to 9, so that means this is 9 volts, and that would be the right answer. Another way I could do it is I could figure out what is the current. That's V over R, 3 over 1. So I have 3 amps here, and then 3 times 2, I'd have 6. Uh, yeah, 3 amps there, which means I also have 3 amps here, which means I have 6 volts. And then I have to add the 3 and the 6 to give me 9 volts over here. Which of these equations is or are correct? This is the same circuit we had for a free response, but it's just, I want to know those equations. So I1 plus I3, that's a junction rule. So I have a I1 coming in there and an I3 coming there and I2. That looks right. Negative 2I1, that's right here, and I'm going in this direction to make it negative. Negative 2I1 minus 8 minus 5I2, that's correct because I'm going with the current, plus 3, that's correct. Here we have 8, that's me going in this direction, minus 2, so I'm going down, minus 2, that says it should be, plus 5I2, I'm going against the current, so that's correct. Alright, so I can get rid of these 3. It's either A or E right now. And then here I have minus 3, so it means I'm going in this direction to get minus 3. Plus 5I2, that's correct, because I'm going against the current right here. Plus 8, plus 2I1, that's correct. Alright, so E is the right answer. So for the circuit, what is I? Okay, this is one of our harder questions, okay? So notice that I, which is an outgoing current, has to equal to whatever currents are coming in here plus whatever is going on here. Um, but if I have 12 amps coming in here and 3 amps, that means I have 15 amps. But I only have 4 coming out, that means I have to have 11 coming here. So in this junction, right here, I have 15 amps coming in here, I have 4 going out, that means I have to have 11 amps coming in there. Now if I have 11 amps coming into this junction, and then a 5 and a 2 as well, that's 11 plus 7, or C is the right answer. These rules for resistors in parallel is correct. They must have the same voltage. As you add resistors in parallel, the voltage in other parallel branches will remain constant. It must have the same current. That's not true. They might not, they could, but they might not. And as you add resistors in parallel, the total current must increase. Okay, all 3 of those are correct. That is A. Which of these rules for resistors is correct? Yes. Not necessarily. They can, but not necessarily. No, actually, that's the opposite. It would decrease. And yes, that is correct. As you add resistors in series, so it looks like 1 and 4. B. All right, 2 resistors are connected with a 5-volt battery. What's the voltage across the 4 ohms? So 5 volt. Let's just draw this. 4 and 6. That gives me a 10 ohm equivalent. 5 volts. That means that the current here is 0.5 amps, 0.5 amps here, 0.5 amps here. that means that here I'm going to have a voltage of 2 volts. Here I'll have a voltage of 3 volts. 2 plus 3 equals 5. So that's the right answer. All right, good job.